So let's say we wanted to solve a differential equation using the method of separation of variables. So for the method of separation of variables, we're going to have some differential equation in the form, so here we're just going to have a function of a. I'm going to have this h function, I'm going to have this h that's a function of x, and here let's have a g as the function of y. And the method of separation of variables allows us to be able to divide both sides by h of x and multiply both sides by b of x, so that way we could get this in the form g of y dy is equal to h of x dx. And at this point what we could do is just integrate both sides and be able to solve for y, which in this case y would be a function of x, looking at this right here. So that's pretty much the method for separation of variables, and we're going to be using it to solve this differential equation, which right here we have dy dx is equal to x over y squared times the square root of 1 plus x. So we could do the same thing here. Right here we would multiply dx on both sides, giving us dy over x. And what we're going to do here, we're going to have the dx right here. We're going to multiply both sides by y squared as well, so that way on the left side we're left with y squared dy. And here we have x over the square root of 1 plus x. So now at this point what we can do is integrate both sides. When we integrate both sides, on the left side, we're just going to get 1 over 3 y cubed. However, because y is a function of x, we could just forget about the constant, and x is just itself. But so when we integrate this part, we're going to actually have to include the constant. So here we could just let u equal to 1 plus x. So that way, when we transform that, we could get u minus 1 is equal to x, so that way we can later substitute in for this x right here, and then du is going to be equal to just d of x. So now our integral that we have is going to be, our x here is going to be u minus 1 over, and then the square root, this is just going to be the square root of u d of u. We could take these apart, and when we do that we get the square root. U over the square root of u is just going to leave us with the square root of u. And then minus 1 over the square root of u. That's just going to be minus u to the negative 1/2 du. And the left stays the same. I could just include the constant right now. So here I just have a constant. And when we integrate this, we're going to get, so the integral of the square root of u is going to be 2 over 3 to the power of 2. U in this case is just our 1 plus x. So here I just have the 1 plus x. Minus, then for here, it's going to be minus 2 times the square root of u, but u is 1 plus x. Then plus our constant. Then 1 over 3 y cubed. And at this point what we can do is just solve for y. So when we solve for y, we get y is equal to the cubed root, and then we're also multiplying 3 on all these terms right here. So on this one we're just going to be left with 2 1 plus x to the 3/2 minus 2 times 3, which is 6, times the square root of 1 plus x, and our constant, plus 3c1. But instead of leaving it like this, what I could do is just take this out. So there we had 3c1. I'm just gonna let that equal to c2. So c2 is equal to 3c1. So that way we could just get all the constants in pretty much one term. And this, just to make that more clear, here would be our function of x that would satisfy this differential equation. So now that we have our solution to the differential equation, what if we wanted to find this differential equation where it passes this point y1 equal to 3? all we're gonna do really is just plug things in. So if we want to do this, we're gonna have to change all the x's in this solution into 1, and it's gonna be equal to 3. So pretty much we have 3 is equal to the cubed root of 2 times, when we have 1 plus 1, we're just gonna have a 2 here to the 3 halves. Then we're gonna have minus 6, and when we have a 1 here, 1 minus 1, it's gonna give us 0, so this term goes away. And we're left with our constant, so plus C2. And all we're really doing is just solving for this constant, which would give us pretty much the equation that passes through this point right here. This is called like the initial value, where we just want it to cross it, really. So solving for this, we could just take the third power of everything. So 3 times 3 times 3, that's gonna be 27, is equal to 2 to 3 half plus c squared. And we could just subtract 27 by this, and there we get our constant. I don't know what this number would be, but this would be what our constant should be. And then we could just go back to our original equation and just change this C2 into this. So now we have plus 27 minus 2, and I'm just going to erase this. We don't really need that. 2 3 halves. So this would be our this would be our solution to the differential equation of this initial value problem. So here we have another differential equation. Again, we can solve it via separation of variables. However, this one's a bit slightly different. You'll see in a bit why. But yeah, we just solve this like normal. So here we have our function of x, here we have our function of y, and we'll just get the y's on the left side and get the x's on the right side. So when we do that, we can divide both sides by y squared and multiply both sides by d of x. When we do that, we get 1 over y squared d of y on the left side, and on the right side we get e to the x squared d of x. I'm actually gonna include a bit more room here. So e to the x squared d of x. Okay. So now we have that. We could just integrate both sides like normal. So bam and bam. On the left side, we're able to integrate just fine. On the left side, we're going to be left with negative 1 over y. So that's just going to be on the left side. However, you could probably see now that when we try integrating e to the x squared d of x, we can't integrate that via normal elementary functions. We would have to do all that polar coordinates, like fancy integration stuff. So in this case, we can't solve for this integral. So this is where definite integration comes to play. And when we use definite integration, we want to be able to include a function of x somewhere. And if we have an initial value condition, we want to use this to our benefit as well. So for our bounds, both of the bounds of these integrals have to be the same. So for our bounds, what I'm going to do is include a 2. So that way when we do all that subtraction and stuff, we actually have a y of 2 on the left side here. And it's going to be going from 2 to x. Again, because I want y as a function of x somewhere, I want to be able to get y as a function of x when we include the bounds in. And again, this one's just going to be the same. However, for this right side, from 2 to x, I'm actually just going to change this x inside the integration into a t. So that way it's a bit less confusing, because when you're going from 2 to the x of e to the x squared d of x, it kind of gets a bit mushed up. It kind of looks a bit weird, I guess. So on the right side, again, we're not solving for this integral. We're just leaving it as it is. It's a general solution. And this is where we include the bounds. So on the left side, we get negative 1 over y to the x. So this is where our y of x comes from. And here we have a minus, so we're gonna have a plus 1 over y to the 2 now. And this is where our initial value condition comes into play. So not only are we solving for a function of, not only are we solving for y as a function of x to actually get a solution for this differential equation, but we're also satisfying this initial condition at the same time, pretty much. And okay, the right side just stays the same. So we have 2x e to the t squared dt. Now you can kind of see where we're going with this. We're just solving for y of x. So here, y of 2 is just equal to 1, and 1 over 1 is just 1. So this whole thing here turns into just the 1, which is pretty nice. And yeah, just solve for y of x. So we get negative 1 over y of x is equal to the integral from 2 to x of e to the t squared dt minus 1. Subtract both sides by, or multiply both sides by negative 1. This turns positive, this turns negative and positive. And we're just going to take the reciprocal of both sides. So now we have y to the x is equal to, I'm going to put the whole thing in brackets, 1 minus the integral of 2x e to the t squared dt to the negative 1. So here you have your solution for this differential equation. And yeah, I hope this video proves helpful for you guys, and yeah, see ya.